Powered Parachute Handbook 2-1 Aerodynamics of Flight. The airfoil is the powerhouse of the powered parachute, akin to a superhero cape that makes it soar. Camber, illustrated in the cross-section, dictates the curvature of the wing, with upper camber on the top surface and lower camber below. The leading edge is the frontal part, while the rear is the trailing edge. The chord line, an imaginary line from front to back, completes the airfoil anatomy. Now, let's delve into the realm of wind, more precisely, the relative wind. It represents the airflow direction in relation to the wing and typically runs parallel and opposite to the powered parachute's flight path. The longitudinal axis, or roll axis, is an imaginary line around which the aircraft rolls, as explained. Unlike a fixed line, it can change due to turbulence and loading alterations. The angle of incidence is the angle formed by the wing's chord line and the longitudinal axis of the powered parachute cart. It can vary during flight due to the flexible line attachment between the wing and the cart. Moving on to this visual, let's talk about pitch angle, the observable angle the powered parachute wing chord makes with the horizontal plane. Don't mistake it for the less perceptible angle of attack. Deck angle, in contrast, concerns the lower frame of the cart concerning the landing surface. Now, if you glance from above, you'll see the planform. There are two types, rectangular and elliptical. The latter, with its curved leading and trailing edges, offers higher performance and efficiency, reacting swiftly to changes but demanding a skilled pilot. Aspect ratio quantifies efficiency, calculated as wingspan divided by the average chord line. Let's talk about wing loading, a term that sheds light on the burden a ram air wing must bear. The formula is straightforward. Divide the aircraft weight in pounds by the wing's total area in square feet. For instance, if a two-seat powered parachute with a 500 square foot wing carries 1,000 pounds, common for two people, the wing loading is 2.0 pounds per square foot. If cruising solo with a 700-pound aircraft weight, the wing loading drops to 1.4 pounds per square foot. Now, enter the realm of gliding flight, a descent with the engine at idle or shut off. The powered parachute has two distinct modes, inflated and deflated. When inflated, it transforms into a ram air wing, displaying the iconic airfoil shape. Conversely, in the deflated state, it resembles a canopy lying flat or neatly packed. For detailed insights on turning the uninflated canopy into a flying wing, our focus here assumes references to the powered parachute wing pertain to an inflated ram air wing already in the airfoil shape. The ram air wing maintains its form thanks to air pressurizing the inside cells via the relative wind, earning it the moniker, ram air wing. The pressure inside exceeds the outside, as dynamic pressure from the relative wind becomes static pressure, rendering the wing more rigid with increased speed. Cross-port openings, strategically placed, connect adjoining cells, ensuring positive pressure throughout and aiding inflation and pressure maintenance in turbulence. The wing, as designed by the manufacturer, retains its consistent shape. However, pilot-initiated turns alter its aerodynamic characteristics, akin to a flap on an airplane. Faster speeds or reduced wing size elevates pressure and, consequently, control forces. Let's delve into the forces governing powered parachute flight: thrust, drag, lift, and weight. In steady flight, all upward forces sum up to all downward forces, and all forward forces equate to all backward forces. The sum of all moments equals zero. Thrust, the forward force generated by the powerplant or propeller, acts parallel to the longitudinal axis. In contrast, drag is the aerodynamic force in the same plane and direction as the relative wind. Lift opposes weight and results from the dynamic effects of the surrounding airstream on the wing. It acts perpendicular to the flight path through the wing's center of lift. The lift equation involves factors like coefficient of lift, velocity, air density, and wing surface area. Lift increases with higher airspeed, increased angle of attack, and greater air density. All wings generate lift through the airfoil shape, creating different velocities over the top and bottom with Bernoulli's Venturi effect. Additionally, there's downward deflection of airflow due to the wing's curvature following Newton's third law. Drag is the resistance to forward motion through the air, opposing thrust. It comes in two forms: induced drag and parasite drag. Induced drag arises from lift production, creating organized circular vortices off the wingtips. Larger and heavier aircraft produce more powerful wingtip vortices. Parasite drag results from various factors like cart, occupants, suspension lines, and skin friction drag of the wing. It increases with surface area and airspeed. Consider the interplay of induced and parasitic drag with changes in the angle of attack and speed. Note the inverse relationship. Induced drag decreases and parasitic drag increases as the angle of attack diminishes and speed rises. Examining the total drag, it peaks at slow airspeeds near the stall, decreases to a minimum at the most efficient airspeed, and then ascends as speed increases. The powered parachute wing is designed to operate above the lowest overall total drag speed, ensuring efficiency. Weight. The gravitational force acting on the powered parachute opposes lift, acting vertically downward through the center of gravity. It encompasses the entire aircraft load, including the wing, engine, cart, passengers, and cargo. In stable level flight, when lift equals weight, the powered parachute maintains altitude equilibrium. The predetermined trim angle and airspeed, set by the weight and wing design, determine the forward airspeed generated. Gravity serves as the primary force propelling the wing through the relative wind during gliding flight. Thrust in a powered parachute serves various purposes, distinct from airplanes. It propels the powered parachute to flying speed during wing inflation and facilitates climbing, cruising, or descending at varying thrust levels. Unlike airplanes, thrust variations have minimal impact on powered parachute airspeed, which remains relatively constant during different flight phases. When thrust equals total drag, the powered parachute sustains level flight, and the relative wind becomes horizontal. Excess thrust, applied for climbing, transforms the relative airstream into an inclined plane, determining the climb rate and angle. The center of gravity, the theoretical concentration point of the aircraft's weight, remains generally in the vertical center of the fuselage. In a two-seat powered parachute, the center of gravity, usually positioned over the rear passenger seat, sees minimal changes with or without a passenger. Fuel tank placement near the center of gravity ensures fuel quantity variations have negligible effects on the center of gravity.